Okay, so in any distance, one can reduce the space from quadratic to linear. And the basic observation is to look on the this graph, right, of dependencies. How do you compute the value in this table in the dynamic program, right? So the idea of the graph again is that for every entry we have arrows from the entry to all the entries that it requires their value to be computed before it can be computed, right? It is a dependency graph. It's fortunately acyclic. It doesn't have cycles. If it had cycles, we would be in big trouble. And it looks essentially like this grid graph we have here with the arrows going from left to right. And we essentially want to compute the cheapest path from bottom right corner to top left corner, where the prices of the edges depends on the cost model that we are in, right? Okay. Now, the important thing is, as we mentioned earlier, is that we always, this is a very simple dependency graph. Every node depends on its three neighbors, above it, to its left, and diagonally, right? So, as such, if we fill this table by column, then it's enough when you compute this arrow to just have, if I want to compute this entry, for example, all I need is that all those values are already computed and the values above it are computed, right? And I really don't care what was in the past, right? We don't care about the history. So if we want, as far as memory, we need to remember only this region of the table. Okay. So I saw this example before, but then I filled it by rows. But one can easily fill them by columns. Let me do one column by example, right? So again, a white cell, we just take the three neighbors. For this one, we take the three neighbors that are to the left, above it, and diagonally. We take the minimum when we add one, right? So this is going to be 2. We're in the unit cost model, right? If it's blue, on the other hand, we take either we copy the diagonal, which is 1, or we take the minimum of the other two neighbors and we add 1. But in this case, we just can copy 1. Here, we also copy 1. And here, we look on three neighbors, 1, 2, 3, their values. Their minimum is, of course, 1. We add 1, we get 2, right? So this fills up this column. Right? And then we can continue to the next column. Right? So this is it. Okay. So as I said, as such, when we fill the table, we just need to know what the previous column is and what the current column is, and we can fill the value of the columns. We have to do them, of course, in reverse direction to the diagonal. Reverse direction to the arrows, right? We go from top to the bottom, and then we move to the next column, right? So we need really to remember only 2 columns when we fill this table. And you remember, all we want to know is the value written in this cell in the corner. So we fill it column by column. We forget the column we don't care about until we reach the last column, and then we get the value that we care about, right? So the benefit of forgetting, it's always good. Okay, so here's the resulting code. Let's look at it a bit more carefully. So it's the same old. So I'm not going to go into this thingy. The important thing is that now we have an array n, and the array n is, it has 2 columns, right? 2 columns. So this goes to m, and this goes 1. N is 1 to m and 1 to 2, right? The second, it has 2 columns. And now what we do is that in every iteration, once we are done filling the second column in this table, we copy it back to the first column, right? And then we go back to the next iteration. And the next iteration, we fill the top of the column, right, and then we continue, right? We just fill it as before, right? And that's all we have to do. Right. So essentially, we remember this is a table with two columns. We remember the last column, and we fill a column, then we copy it back and we repeat. So not very interesting. Right. The running time is still mn, so we didn't save anything, but the space was reduced from nm to O of m, and we really care about this, right? Because as I showed in my, as I mentioned earlier, edit distance sometimes is used on huge strings in the tens of thousands of characters, and then, the table becomes in the millions or billions of entries, and then saving memory has real impact on running time because of a caching procedure, not to mention that you might even run out of memory in some cases. Okay. One thing to mention is that this just compute the cost of the optimal alignment or the optimal edit distance for the two strings, but it doesn't give you the edit distance itself. So what edit operation you need to perform. So computing those edit operations using the linear space or near linear space require quite a bit more work. One can do some things, but they're a bit more complicated. You can see Jeff Erickson's book, I think, has this. Otherwise, it appears in Tardosh book, Kleinberg Tardosh book. If you're interested, we're not going to spend too much on that. You can, in fact, think about how to do it. It's a very nice exercise. Okay, this is it for now.